So in chapter 3, we started out by discussing the fact that we really don't have a good, maybe we haven't had a good concept of the smallest particle of matter, smallest piece of matter, whether there is a smallest piece of matter, whether everything is continuous. We started by talking about J.J. Thomson's discovery of the electron and Millikan's further contribution to the properties of the electron. And then we went on to talk about the unknowns in the observation, in the empirical observation of line spectra, and to the more complicated blackbody radiation and Planck's contributions to blackbody radiation that added to the concept of this quantization of perhaps matter and energy. And then we moved on to photoelectric effect and Einstein's contribution to the quantization of photons, of light and energy. And then Compton's experiment where he was able to confirm Einstein's hypothesis. And so one of the things that's built in here is that there's the quantum mechanics of energy, light and energy, but there's also the quantum mechanics of atoms and particles. And we haven't really looked at the quantum mechanics of atoms. So that's really where we want to go to now, is continue with the development of quantum mechanics by looking at the model of the atom, and let's do so through a slightly historical approach. So we'll start with this concept of the plum pudding model, and then of the solar orbits model, and then of the quantum mechanical sort of fuzzy model of the atom, each of which is shown here. What is the atom? That's the question, is what is the atom? What does it look like? How can we model it? How can we describe it? What is its structure? Arguments started long before the 1900s, which is when a lot of this was theoretically resolved. Of course, we may learn new things we will always learn new things going forwards. But what is the model of the atom? Arguments started long ago. We have recorded arguments from Democritus in 400 BC, where Democritus says that the atom is... Sorry, I don't know where I left off with that sentence. So Democritus, 400 BC, coined the word atomos, therefore, hence that's where atom comes from, which in Greek means not to cut, indicating that atomos is the smallest possible thing, whatever atomos is. Now, we know today that the atom is not the smallest possible thing, but it is the smallest reasonable, to some extent, it is often the smallest thing that we deal with. Atoms, then molecules, then things. But what's interesting is that that Aristotle comes along soon after and says and doesn't agree with Democritus and says that everything is continuous. And Aristotle, being the big bully he is, sort of is the guy who everybody remembers. I don't know. Maybe it's because he's smart. I don't know. But this idea that everything is continuous, that there is no such thing as a smallest thing, that's really what everything is continuous means, really did hang around for another 2,000-ish years. It wasn't until the 1600s when somebody corrected Aristotle finally, and it was Dalton, who was a Newtonian, right? He followed Newton in the 1600s. And Newton, remember, actually was somebody who proposed that light is a particle. He actually did that. But Dalton, who was a Newtonian, said that it used atoms to describe gases' behavior. So Dalton actually was able to show that things must be made up of these little particles called atoms. He didn't necessarily show that they were the smallest possible thing, but he revived the idea of the atom. And then that sat for a while until Thomson comes along and discovers something smaller than the atom. Nothing was really understood to be smaller than the atom until Thomson's discovery of the electron. Remember, now he's discovering something that clearly has mass, that has size in the way that he measured it, that was smaller than anything we had ever seen before. So the discovery of the electron made Thomson realize that there's something smaller than an atom. Just as a reminder, he did this with experiments with cathode rays in a cathode ray tube, discovered that there was a small particle that was being created, and that all these particles had the same charge to mass ratio. That was the Thomson experiment, J.J. Thomson. And so Thomson further went and described now a model of this atom with his electrons. And it's called the plum pudding model. It's our first model of the atom. It's the plum pudding model. So we see here in the upper left-hand corner a representation of the plum pudding model. When Thomson discovered the electron, he realized it was some small part of this atom that we sort of realized that we did know by 1897 existed. And Thomson just imagined that the electrons were stuck in the atom like plums in a plum pudding. Plum pudding was a standard dessert or thing that people ate in the end of the 1800s. I don't know if you've ever had a plum pudding, but it's like a blueberry pie or something like that. So this is the plum pudding model. The details of the plum pudding model are that it was somehow J.J. Thomson understood that there was more than one electron in an atom, but it was definitely understood at the time that atoms were generally neutral. They weren't always neutral, but atoms are often neutral. And so if there are these negatively charged, and ignore these other pictures, if there are these negatively charged particles in an atom, then there must also be positive charge in an atom. And J.J. Thomson's best description was that the pi itself is the positive charge and the negative charges are just stuck in there. So the positive charge is just evenly distributed about the atom with the little negative dots stuck in various places, such that the sum of the pluses and the minuses is 0, or somewhere close to 0 if we ionize the atom, right? If we take out, ionizing the atom is taking out a minus charge, and so we know that the atom is now positively charged. I guess that was also understood, that you could ionize atoms, you could take out some of the negative charge and make them positive. That, of course, was done by Millikan. Millikan did that in his experiment in order to measure the charge of the electron. He ionized the atoms. He took out electrons and was able to measure the leftover positive charge from an atom that was originally neutral in order to figure out how much negative charge he had taken out. That was Millikan. Right? So putting together the concepts of Millikan and J.J. Thomson, we can say, okay, maybe the plum pudding model is a reasonable model of the atom. And so in this chapter, the first real discovery that we'll look at in detail is the discovery of the nucleus, which changed the model of the atom, right? So the discovery of the nucleus made us go from the plum pudding model to the solar orbits model, right? The solar orbits model that electrons were orbiting some kind of smaller nucleus. And that's the discovery of the nucleus by Rutherford. And we will go into more detail on that in the next class. Discovery of the nucleus and the new model of the atom, which is the model that we often use today, but it's not a quantum mechanical correct model.